In physics, symmetry refers to a transformation of a system that leaves some aspect of the system unchanged. Imagine shifting an object in space. If its properties stay the same, we have translational symmetry, or think of rotating a sphere. It looks identical regardless of the angle, demonstrating rotational symmetry. Even the idea of time flowing backward can be a symmetry. A ball bouncing without friction would behave the same way whether time runs forward or in reverse. Why does symmetry matter so much in physics? Well, for starters, it's fundamentally linked to conservation laws, a concept elegantly described by Noetherstheorem. This theorem tells us that for every symmetry, there's a corresponding conserved quantity, translational symmetry in space. We have conservation of momentum, symmetry across time. That means energy is conserved. How about rotational symmetry? That translates to the conservation of angular momentum. Symmetry isn't just about conservation laws. It's a guiding light when physicists build the fundamental theories that describe our universe. Think about Einstein and special relativity. He built his theory on the idea that the laws of physics are the same for everyone moving at a constant speed, and that the speed of light is always constant. These are symmetries that shaped the way we understand the universe. Symmetries also help us make predictions. In the 1960s, physicists used a concept called the eightfoldway, based on symmetry principles, to organize the chaotic zoo of particles they knew about and even predict the discovery of new ones. More recently, the tantalizing idea of supersymmetry, a hypothetical symmetry between different types of particles, suggests that a whole range of undiscovered particles might be out there. But sometimes, the most profound discoveries happen when symmetries break. Think about water freezing into ice. A perfect liquid with translational symmetry transforms into a crystal with a fixed structure. Or consider the famous Higgsmechanism, which breaks a fundamental symmetry and is the reason particles have mass in the first place. Symmetry weaves its way through all branches of physics. Crystallographers use it to decipher the beautiful patterns of atoms and crystals. Optics relies on symmetries in the ways light reflects. Quantum mechanics finds deep connections between symmetries and how atoms and molecules behave. Even cosmologists study the vast, nearly uniform universe, guided by the idea of large-scale symmetries. Symmetry is a profound idea. It reveals conservation laws, shapes our fundamental theories, hints at new particles, and allows us to understand the very building blocks of reality. And the exciting thing is, physicists are still pushing the boundaries of symmetry. There are always deeper connections and hidden patterns waiting to be unveiled. That's a wrap for today's topic. I hope you enjoyed. Thank you for watching.